Well, now I'll talk about direction fields. And the idea is that although it may be hard to solve a differential equation, we may not know how to solve it, we can look at the graph of a first order differential equation without knowing the solution first. And to see this, let's consider this differential equation. dy dx equal to negative 2y. We don't know what the solution is yet. We haven't discussed how to find these solutions. But we can figure out the slope of the solution at any given point because the slope is the derivative. So we have a nice formula for the slope. The slope is given by negative 2y. So if we're given a point, we can find the slope at that point. So let's see if we can go about doing this. So here I have a list of values for x and y. I let x be equal to 0.5 and then I changed the values of y. And I want to find the slope at each of these points. dy dx, the derivative, which we know is negative 2y. So for the first point, negative 5.1, the slope would be negative 2y, or negative 2 times 0.1, which is negative 0.2. We can continue. The next value, the y value is 0.5, so negative 2 times 0.5 is negative 1. And we can continue this to fill in the rest of the table. As far as the graph goes, I have the points that we looked at, and now we're just going to put these little line segments at each of the points that indicates the slope. And we're just going to keep doing this. So here I let all the values of x be 0.5. Next we would want the values of x to be 1 and fill in the 1 part of this graph. We could then let x be equal to 1.5, x be equal to 2, etc., and we get a bigger and bigger picture. So if we were to continue this process, and for a lot of points, we would get something that looks like this, with all of these little line segments that show you the general direction of the slope at particular points. And this can help us visualize solutions. So let's suppose we knew a single point. Let's suppose we knew that if x is 0, y is 1. So we have this point here. Well, we can draw a solution. We just kind of generally follow the direction of these arrows. And we would get something like this. And here it is formally without my horrible drawing skills, where we can see that it passes through the point x0, y1. And then we can get these general solutions and see what the graphs look like. So now I want to look at graphing these direction fields using this program called Dfield. So in order to use Dfield, over here on the left, we start by typing in our dependent variable y. It already inserts the prime because we want the derivative. On the right-hand side, we give the function. So ours was y equal to negative 2y. And then we have our independent variable, which is x. And you can change the minimum and maximum for y and click Graph Phase Plane. And now we have the graph that I had looked at before. And we talked about the initial conditions starting at 0, 1. And if I just click the point 0, 1, I can graph the solution. And if we change that starting point, the point that we know, we can get different graphs. So we see several here. We can move down to the bottom. And we get lots of different graphs. So there are lots of different solutions to this differential equation. It really just depends on the initial condition. What point did we start with? Let's look at another one. This time we'll do x squared plus 2y. We see a much different graph this time. And once again, we can click different starting points and see what these solutions look like. So we can see that these are looking very different. If I start something down here, it looks very, very different. And so these direction fields are designed to just give us these quick, short views of what the solutions might look like. And using computer programs, we can start to see what the solution curves may look like in these direction fields. So even without the actual solution, we don't have the solution to this differential equation, we can get a general idea of what the solutions might look like.